In most nuclear decay processes, large amounts of energy are released during the reaction, and oftentimes that energy comes in the form of gamma emission or the emission of something called gamma rays. These are not particles per se, but rather something more similar to light or ultraviolet radiation or X rays, but supercharged gamma rays are much more dangerous than even X rays. They're much more powerful, they're much more energetic. We can see that a little bit with what we call the penetrating power of each one of the particles that we've talked about so far in our lessons on nuclear decay. Alpha particles are generally pretty slow moving. They're heavy helium nuclei. If you hold a piece of paper up in front of an alpha particle, chances are your alpha particle will stop it. Beta particles, on the other hand, have a lot more energy, are moving faster, could go through the paper, but might be stopped by a piece of plastic. Energetic, yes, but not close to what we see with gamma rays. Gamma rays are so powerful, so energetic, that they can penetrate paper, they can penetrate you, they can penetrate metals like steel and lead, and therefore these are the things that you have to be most concerned about when you're dealing with radioactive material. The amount of energy given off, it can be severely damaging to tissue, and so humans don't want to be exposed to any gamma radiation. At least they want to be exposed to as little as possible. So, with that, let's just do a quick summary of everything that we've seen. We've seen alpha emission, where a helium nucleus is produced, reducing the atomic number in our daughter isotope by 2. The mass number goes down 4 compared to the parent isotope, and your number of neutrons is also going down by 2. In beta emission or beta negative emission, the atomic number actually goes up by 1, but the mass number does not change. In positron emission, which we also call beta positive decay, the atomic number goes down by 1, but the mass number does not change. Gamma emission accompanies many of these processes, but it's often not written. Does not change the atomic number or the mass number. It's just a release of a massive amount of energy. In electron capture, an inner shell electron is captured by a proton in the nucleus, causing it to become a neutron essentially, which decreases the atomic number by 1, but increases the neutron number by 1, and therefore the mass number does not change. Okay, let's get to work on practicing on writing these nuclear equations. See you soon.